Welcome to today's paper reading. Today's paper is titled, R.A.C.E. Robust Adversarial Concept Erasure for Secure Text-to-Image Diffusion Model. This paper was published on AR14 by Changhoon Kim and colleagues from Arizona State University and Intel Labs. The abstract highlights the challenges faced by text-to-image diffusion models in generating high-quality images while avoiding the reproduction of sensitive content. To tackle this issue, the authors introduce robust adversarial concept R.A.C.E, an innovative approach that enhances the robustness of concept erasure methods. R.A.C.E employs an adversarial training framework to identify and mitigate adversarial text embeddings, leading to a significant reduction in the attack success rate, ASR. Specifically, R.A.C.E achieves a 30 percentage point reduction in ASR for the nudity concept when compared to the leading white box attack method. The extensive evaluations show R.A.C.E's effectiveness in defending against both white box and black box attacks, marking a substantial advancement in protecting text-to-image diffusion models from generating inappropriate or misleading imagery. This work emphasizes the critical need for proactive defense measures in the rapidly advancing field of adversarial challenges. Text-to-image (T2I) diffusion models are capable of generating high-quality images from textual descriptions. These models are trained on extensive datasets, which can include copyrighted, explicit, and private materials. This capability can lead to the inadvertent replication of protected images, posing a risk of misuse for misinformation or public opinion manipulation. To address these content security issues, concept erasure techniques have been developed to remove specific concepts from T2I models. However, these techniques are vulnerable to reconstruction, highlighting the need for more robust methodologies to ensure the integrity of content generation. Figure 1 provides a comparative view of concept erasure methods within text-to-image (T2I) diffusion models. The Erase Stable Diffusion (ESD) method successfully removes targeted concepts from the original Stable Diffusion (SD) outputs. However, these erased concepts can be reconstructed using the unlearned if method. In contrast, our proposed robust adversarial concept R.A.C.E method demonstrates enhanced robustness against such red teaming reconstruction efforts, ensuring that the erased concepts remain effectively removed. In the field of text-image (T2I) synthesis, generative models have advanced significantly, enabling the creation of highly realistic images from textual prompts. Fine-tuning techniques have been developed to customize these models for specific user needs, but this also raises concerns about potential misuse, such as spreading misinformation. Concept erasure in T2I diffusion models focuses on removing sensitive or copyrighted concepts. Techniques like fine-tuning model weights to exclude these elements have been proposed, but red teaming has revealed vulnerabilities where erased concepts can be regenerated. Robustness evaluation through red teaming strategies has shown that some safety measures can be bypassed, necessitating the development of more effective countermeasures. Our work addresses these challenges by introducing a novel defense strategy against prompt-based red teaming attacks. The methodology presented in this paper focuses on expunging target concepts from text-to-image (T2I) diffusion models through an adversarial training framework. This framework is designed to robustly erase specific concepts. The method is built upon the Stable Diffusion Model (SD), which includes an image autoencoder and a UNet-based diffusion model that conditions on text embeddings. A key innovation is the single time-step adversarial attack, which optimizes the text embedding to regenerate images by introducing perturbations at a single time step. This approach is evaluated through the attack success rate, ASR, demonstrating the feasibility of reconstructing erased concepts even with attacks confined to a single time step. Figure 2 showcases the efficacy of single time-step adversarial attacks in the context of concept erasure within text-to-image (T2I) models. The figure presents the attack success rate (ASR) across different time steps, accompanied by representative images that demonstrate the effectiveness of these attacks. Notably, even when the adversarial attack is applied at a single time-step T** operator, the perturbed text embedding C plus delta T** operator is capable of reproducing images that contain the previously erased concept. This finding underscores the potential vulnerabilities in current concept erasure methodologies and highlights the need for more robust adversarial training strategies to enhance the resilience of T2I models against such attacks. For a detailed understanding of the methodology and results, please refer to Section 3.2 of the paper. Table 1 presents a performance comparison between R.A.C.E and R.A.C.E, two methods for concept erasure in T2I models. R.A.C.E achieves an FID score of 33.12 and a CLIP score of 0.726. In contrast, R.A.C.E demonstrates superior performance with an FID score of 25.16 and a CLIP score of 0.745. Notably, R.A.C.E shows promising reductions in the attack success rate, ASR, for nudity prompts within the I2P dataset, indicating its effectiveness in enhancing the robustness of concept erasure mechanisms. Additionally, R.A.C.E improves image quality metrics, as assessed on the MS-COCO dataset, highlighting its strategic advantage in adversarial training scenarios. The experimental evaluation of the R.A.C.E framework involves assessing its performance across various datasets, including artistic styles, explicit concepts, and identifiable objects. Key hyperparameters are standardized to ensure a uniform image generation process. The training details focus on using the R.A.C.E Stable Diffusion (ESD) model with specific attack parameters and optimization techniques. To rigorously test R.A.C.E.'s robustness, a suite of adversarial attacks is deployed, spanning both white box and black box approaches. Figure 3 illustrates the effectiveness of R.A.C.E in defending against the reconstruction of explicit content by state-of-the-art red teaming methods like Indepth. While ESD significantly reduces the chance of generating images with exposed body parts, Indepth can bypass ESD's defense mechanisms. In contrast, R.A.C.E maintains its robustness against such sophisticated attacks, showcasing its advanced protective capabilities and safeguarding against the regeneration of sensitive content. Figure 4 demonstrates R.A.C.E.'s ability to precisely erase specific concepts without affecting unrelated elements. The diagonal images show the targeted erasure, while the off-diagonal images illustrate the preservation of other concepts. Baseline images from the original Stable Diffusion model are included for comparative purposes, highlighting R.A.C.E.'s effectiveness in maintaining image integrity while removing targeted concepts. Table 2 presents a comprehensive comparison of the attack success rate, ASR, against both white box and black box attacks, focusing on various concepts including artistic styles like Van Gogh, explicit concepts such as nudity, violence, and illegal acts, and objects like church, golf ball, and parachute. The table highlights that R.A.C.E significantly reduces ASR by over 30% in absolute value for Van Gogh, nudity, and church when compared to the previous state-of-the-art attack method, Indepth, 72. However, the reductions in ASR for violence and illegal acts are less pronounced. Despite these variations, R.A.C.E maintains high image quality metrics, indicating its effectiveness in enhancing robustness without compromising the fidelity of the generated images. Table 3 presents the accuracy of erased and non-erased classes in the ImageNet dataset, focusing on the evaluation of ASD and R.A.C.E methods. The study generates 5,000 prompts with varied random seeds to produce a diverse set of images, which are then evaluated using a pre-trained ResNet 50 classifier for top 1 accuracy. The results indicate that R.A.C.E shows improved capability for object concept erasure compared to ESD, although there is a slight decrement in classification accuracy for non-target classes, likely due to R.A.C.E.'s method of targeting the neighborhood surrounding the intended concept. Table 4 presents the results of ablation studies aimed at improving performance by evaluating the effectiveness of adding weight regularization and closed concept keywords using the nudity concept. The performance is assessed through ASR, attack success rate, and quality metrics such as FID, freshet inception distance. The methods compared include R.A.C.E with regularization, R.A.C.E plus reg, and R.A.C.E with keywords, R.A.C.E plus keywords. The data indicates the impact of these modifications on the ability to handle the specified concept while maintaining overall model quality. In this work, the authors present R.A.C.E, a novel defense approach designed to protect text-to-image stable diffusion models from prompt-based red teaming attacks. R.A.C.E effectively strengthens the model's concept erasure capabilities while maintaining computational efficiency, offering a valuable enhancement to the current erasure framework and bolstering defenses against various adversarial techniques. The authors also observe the robustness quality trade-off and discuss possible future directions to improve it. This initial contribution lays the groundwork for further exploration, underscoring the critical importance of developing sophisticated defenses in the rapidly evolving domain of generative AI. The authors would like to express their gratitude to Sang-Min Young for assisting with the experiments. This work is partially supported by the National Science Foundation under grant number 2038666 and number 2101052. The views and opinions of the authors expressed herein do not necessarily state or reflect those of the funding agencies and employers. Thank you for watching.